Command decision at sea is rarely a choice between a good option and a bad option. In the high friction zone of naval combat, the choice is almost always between two catastrophic outcomes, and the captain must calculate which disaster offers the lower price tag in human lives. On the evening of April 9, 1940, the commanding officer of the German light cruiser Karlsruhe faced exactly this calculus. He stood on the bridge of a crippled flagship, 13 nautical miles off the coast of Norway, drifting without power in waters where British submarines were known to operate. His choice was stark. He could attempt a slow, desperate tow operation that would leave his crew and the rescue ships exposed as stationary targets, or he could destroy his own vessel. Carlsruhe was a significant asset, a Königsberg-class light cruiser built as a weapon, not a symbol. She carried 9 6-inch guns in 3 triple turrets, 1 forward, 2 aft, and those aft mounts sat in a distinctive offset that widened their firing arcs. On this day, she led the group striking Kristiansand during Operation Weserübung, put her assault troops ashore, and then turned for Germany, driving hard through the Skagerrak to outrun the combat zone. But the British submarine service had established a blockade line to intercept the returning German fleet. The submarine Truant lay in wait, submerged and silent. When the Carlsruhe crossed the firing solution, as the British commander released a spread of torpedoes, most missed. One warhead struck the starboard side amidships, punching through the light belt and detonating in the spaces that kept the ship alive. The violence of the explosion crippled the cruiser's nervous system. Propulsion failed. Electrical generation was badly disrupted. Power to some of the pumps fighting the incoming water was cut, and the ship's options collapsed from minutes to hours. Steering was compromised, and the ship began to list. That brought the captain to the only decision that mattered. The cruiser was not sinking fast, but she was dead in the water. A tow would take hours, and hours meant exposure in a sector where the attacker could still be waiting. He judged the risk to the escorting boats and to his own crew as unacceptable. So he traded steel for lives and ordered an evacuation to the torpedo boat Greif. Once the transfer was complete, Greif pulled clear and swung her tubes back toward the cruiser. This was not an accident and not panic. It was scuttling, a deliberate demolition meant to guarantee the ship could not be captured, salvaged, or repaired for the enemy. Greif fired 2 torpedoes into Carlsruhe. The hull shuddered, steel groaned under the new Uder, and at last, buoyancy gave up. As the cruiser slipped beneath the surface, she began the long fall toward the seabed. For most warships with flooded hulls and top-heavy turrets roll on the way down, arriving broken or inverted. Carlsruhe did not. Whatever happened in the darkness, she settled upright, on her keel. The ship vanished from the surface world, leaving only an oil slick and the churning wake of the retreating escorts. For decades, naval historians held only approximate coordinates, and the ocean floor is vast and unforgiving of imprecise records. Down in total blackness, and the cruiser sat where she had landed, upright, silent, and uncharted. She became a hazard, but not in the way her captain intended. She was no longer a threat to British shipping. She was now a latent threat to a different kind of vessel, one that would not be built for another 30 years, 15 meters, 50 feet. That is the entire margin of error separating a piece of critical modern infrastructure from a catastrophic industrial accident. In the featureless plains of the ocean floor, a distance of 50 feet is statistically zero. It is a navigational rounding error, yet for more than 4 decades, a high-voltage power cable carrying electricity between Norway and Denmark has pulsed with energy exactly that distance away from the jagged, rusting steel of a light cruiser. The environment at this location is defined by the physics of the deep hostile. The seabed lies at a depth of 1,600 feet. At this level, the ocean is a crushing, lightless void. This is the domain of hydrostatic pressure. For every 33 feet of depth, the weight of the atmosphere adds another 14.7 pounds per square inch of force. By the time one reaches the bottom of the Skagerrak Strait, the water exerts over 700 pounds of pressure on every square inch of surface area. This force is relentless. It compresses gases, shatters weak voids, and forces water into the microscopic pores of any submerged material. To operate in this zone requires specialized engineering. It is not a place for casual visitation, But humanity requires connection, and the seafloor is the only available corridor for the massive copper and steel umbilicals that power national grids. In 1976 and 1977, engineers laid the first Skagerrak direct current power cables across this stretch of sea, and they deployed the heavy cable from a surface ship, paying it out mile after mile, trusting their charts and their depth sounders. They did not know what lay in the darkness below them. They were working blindly along a cable route, a mapped corridor where anchoring and bottom contact fishing are tightly restricted to protect the link. The corridor exists to reduce risk, to keep steel and nets away from the line. The irony is that the cable layers, in their effort to create a safe zone, threaded their line directly past a massive, unmapped hazard. Had the cable draped over the wreck's sharp superstructure, the cruiser's steel would have worked like a serrated blade. Over time, current and vibration could have sawed through insulation, shorted the line, and cut the power link between two nations. But the lay missed the wreck by 50 feet. The wreck lay there, silent and undetected, while the cable hummed with energy for decades. Its posture on the bottom made it a fortress-like obstacle on a flat plain, a permanent neighbor to the line. This proximity created a unique constraint for any future survey. Usually, when a wreck is found, salvors might drag a sonar sled low over the site or use grappling hooks to recover samples. In an infrastructure corridor, those methods are illegal. You cannot risk snagging the active power line. The presence of the cable meant that this specific patch of ocean was effectively a no-fly zone for heavy physical contact. The wreck was guarded not just by the crushing pressure, but by the legal and technical wall of the power grid. The status quo remained undisturbed until routine maintenance technology improved. Statnett, the operator of the grid, began using advanced acoustic scanning to inspect the integrity of their line. They were looking for scour, where the current washes away the mud supporting the cable, or for physical damage from illegal trawling. They were not looking for history, but on the scrolling monitors of the sonar team, the flat monotony of the seabed was suddenly broken. A massive, hard acoustic shadow appeared on the screen, rising up from the mud right next to their vulnerable asset. Sound is a blunt instrument for history. When engineers map the seabed with acoustic energy, the return gives them geometry, not color, contours without texture, mass without identity. It can show what breaks the flat baseline of the ocean floor, but it cannot read a nameplate or recognize a flag. In 2017, Statnett's sonar operators logged the anomaly during a routine inspection of the Skagerrak cable. The data showed a hard, elongated object, clearly man-made, sitting uncomfortably close to the line. For 3 years, it remained a digital ghost, pixels that hinted at a wreck but proved nothing. To manage the risk to the power grid, the engineers needed to know exactly what they were dealing with. A pile of discarded shipping containers presents a different hazard profile than a warship loaded with unexploded ordnance. In June 2020, Statnett chartered the offshore survey vessel Olympic Taurus to return to the site. The mission was not an archaeological expedition, it was a technical risk assessment. The goal was to visually inspect the anomaly and determine if it posed a threat to the stability of the cable connection between Norway and Denmark. Then the first pass used multibeam sonar, painting the seabed into a high-resolution point cloud as Olympic Taurus moved over the corridor. The new scans locked in the target's proportions: a long hull, a sharp bow, and a defined superstructure. Unmistakably a ship, but still unnamed on the screen. To bridge the gap between a shape on a screen and a positive identification, the team deployed a remotely operated vehicle, or ROV. This is the workhorse of the modern subsea industry. The ROV was a boxy subsea workhorse, thrusters, arms, and high-definition cameras, tethered to the ship by an umbilical that carried power down and data back up. On deck, the pilots lowered it into the water and began the descent. Light faded to nothing. At this depth, reality existed only where the floodlights could cut it out of the black. The operation required extreme precision. The pilots were flying a heavy piece of industrial equipment in a current, right next to a live power cable that could not be touched. One mistake with the thrusters could tangle the umbilical or impact the artifact they were trying to inspect. They had to find the wreck without disturbing it. As the ROV reached the bottom, the sonar indicated the target was directly ahead. The pilots pushed the machine forward, fighting the drag of the long tether. Suddenly, the darkness in front of the camera cleared. The intense LED floodlights washed over a wall of steel plating. It was not a rock formation. It was the vertical side of a massive warship standing upright on the keel. The hull was coated in a thin layer of marine growth, but the metal underneath was intact. The ROV hovered there, suspended in the current, looking at a ghost from 1940. The engineers had found the ship, but to prove which ship it was, they would need to fly up and over the rail into the structure itself to find a fingerprint that matched the historical record. The distinctive geometry of a warship is as unique as a fingerprint. While many destroyers and cruisers from the 1940s look similar to the untrained eye, naval architecture contains specific structural DNA that cannot be faked. As the remotely operated vehicle moved along the sediment, the pilots and the archaeologist Frode Cavalier were looking for one specific mutation in the design that would confirm the identity of the wreck. They found it on the aft deck. Most warships keep their aft turrets on the center line, stacked for balance. The Königsberg design broke that rule. The aft mounts were stepped off center. It was a signature detail the class could never hide, a silhouette-level fingerprint waiting to be matched in the dark. On the screen in the control room, the lights of the robot illuminated the massive steel housings of the 6-inch guns. They were not inline, they were stepped, just as the blueprints dictated. The barrels were still trained out, frozen in the position they held when the crew abandoned stations 80 years prior. This architectural quirk confirmed the class of the vessel immediately. It was a Königsberg. But to prove it was the Carlsruhe and not one of her sister ships, the team needed a more specific marker. The robot thrusters hummed as the machine drifted further aft toward the stern. The water at 1,600 feet is low in oxygen and cold, as a combination that acts as a preservative. The corrosion that eats ships in shallow, warm water is slowed significantly here. The teak decking had rotted away, but the steel hull plates were intact. The portholes were open. The ship looked less like a wreck and more like a vessel that had simply been parked in the dark. The final piece of evidence waited on the stern shield. In the German Navy of the era, capital ships often carried a large crest on the stern, usually a national eagle surmounting a swastika. In many shallow water wrecks from this period, these symbols have been removed, destroyed by corrosion, or lost during the violence of the sinking. The camera zoomed in on the vertical steel plate at the very rear of the ship. The image on the monitor sharpened. There, clearly defined in the metal, was the emblem. The swastika was perfectly preserved, a chilling and unmistakable stamp of the regime that built her. It was not covered in barnacles. It was sharp, angular, and undeniable. This visual confirmation closed the case. The length of the hull measured 570 feet. The offset turrets matched the class. The location matched the British patrol reports, and the stern crest confirmed the nationality and the era. The acoustic shadow was officially identified as the German light cruiser Carlsruhe. The discovery solved the mystery of the disappearance, but it instantly crystallized the engineering problem. The ship was not a debris field. It was a solid, heavy, upright structure that could still contain ammunition and trapped pockets of fuel oil from another era, and it was sitting within striking distance of the power cable that kept the lights on in Denmark. The survey had achieved a forensic success, but it had revealed a precarious physical reality. The wreck was stable for now, but the margin of safety was terrifyingly small. To salvage a warship of this magnitude from the bottom of the ocean is an act of violent physics. The Carlsruhe is 570 feet long and displaces thousands of tons. She is not merely resting on the seabed, she is embedded in it. After 8 decades, the sediment has acted like a heavy glue, creating a powerful suction seal around the hull. To break that seal requires force that far exceeds the dead weight of the steel itself. A salvage engineer would need to apply massive hydraulic tension to snap the ship free from the mud. In the open ocean, this violence is acceptable. But in the Skagerrak Strait, the margin for error is non-existent. The decision to recover the vessel was analyzed not just by archaeologists, but by the engineers responsible for the power grid. They looked at the geometry of the site and the proximity of the Statnett cable. The math was unforgiving. The high-voltage line runs alongside the wreck's starboard flank at a distance that barely qualifies as separation. That is the constraint. Any lift would inject dynamic energy into a static site. The hull could swing, crumble, or worst of all, slide sideways, and a slide of 50 feet would bring armored steel into the cable. The repair is a nightmare scenario. Specialized cable ships would have to recover both ends, lift them to the surface, splice them, and lay them back down, all while working in the shadow of the wreck itself. The true cost is not just money or time. It is a weakened grid, a broken interconnector, and a long window where failure has fewer backups. Faced with that trade-off, the decision-makers chose absolute containment. The wreck was safer as a tomb than as an exhibit, stable where it sat, dangerous only if disturbed. The corridor's logic prevailed. There would be no cutting, no lifting, and no experiments, just a single rule that closed the case. No touch. Steel is not a permanent material, even in the cold, oxygen-starved waters of the Skagerrak Strait. The chemistry of the ocean will eventually win. The cruiser Carlsruhe is currently stable, standing upright on her keel as if ready for inspection, but she is slowly returning to the mineral state from which she was forged. This process is the long risk shadow of every shipwreck. As the metal thins over the coming centuries, and the superstructure will collapse, the guns will fall silent into the mud, and the hull will fold in on itself. But for now, the ship remains a fortress of 1940, guarding a patch of darkness 1,600 feet down. The identification in 2020 changed how the site would be treated. This was no longer an anonymous sonar anomaly. It was a state warship, a place that demanded the restraint people associate with a war grave. And while it lies near the Norwegian coast, under Norway's safety jurisdiction, widely recognized principles of sovereign immunity generally presume a sunken state warship remains the property of its flag state unless formally abandoned. For the families of the crew, the discovery offered a specific kind of closure. Carlsruhe is no longer missing. She is located. Coordinates replaced rumor. The last moments are no longer a story carried in albums and archives, but a place fixed in the black, recorded by the hard gaze of survey cameras. For Statnett, the operator of the power grid, the legacy of the mission is one of vigilance. The cable and the cruiser are now locked in a permanent standoff. The high voltage line continues to pulse with energy just 50 feet away. It is a critical artery for the modern world, carrying electricity that can help balance a lower carbon grid between nations, while the instrument of a past war sleeps next to it. The engineers cannot move the wreck, and they cannot move the cable. Instead, they have placed the site on a permanent watch list. Every few years, the survey ships will return and remeasure the standoff. Not to chase history, but to confirm that the distance has not shrunk, that sediment has not shifted, that the cable has not migrated towards steel. The two will remain locked in this proximity for decades, perhaps centuries. The decision to leave the Carlsruhe untouched was the only logical conclusion to the survey. To lift her would be to risk the power supply of millions. To cut her would be to desecrate a grave. So she stays. The lights of the robot have faded, and the noise of the thrusters has gone. The silence has returned to the deep. The cruiser stands in the black water, a steel monument to a violent afternoon in April 1940, holding her station forever in the blind spot of the North Sea.